You guys asked for this a lot, so today we're finally covering triplanar mapping in Copernicus. This turned out to be much trickier than I anticipated. So I first have to give some credit where credit is due. Most of my setup is based on 2 Unreal Engine tutorials by Visual Tech Art, but I also picked up some smaller tips from videos by Luca Veronese and Rowan Dalby, and you can find links to all of them in the description. Also, this will be a 2-parter. In this video, we'll build the main setup, and in our next free tutorial, we'll build an add-on for dealing with normal maps, which are a whole new challenge in and of themselves. But now, let's get going. This is the setup that we're going to build today. It will consist of 4 main parts. In the first part, we're simply going to import some attributes as maps into Copernicus. The second part, we're going to create a set of 3 UV maps, 1 UV map for each projection axis. In the third part, we're going to create a mask for each projection axis, a mask that we later use to blend those different projections. This is exactly what we're going to do in the fourth part, and this will give us a triplanar mapping in the end. So let's take a look at how we can build this. In an empty scene, I'm going to bring in a GeoNode. I'm going to dive inside. And as a test geometry, I'm going to load in the rubber toy. On this rubber toy, I want to disable add shader, and I want to give it 1 level of subdivision. And I also want to give it some normals, since this is one required attribute that we need for this setup to work. The second required attribute will be some UVs, because this still is Copernicus, and Copernicus needs UVs to work properly. But these can be fairly quick and dirty UVs, because again, we're using triplanar mapping here. Triplanar mapping will hide our UV seams. We're done here. Let's drop down a null. Let's call it N. Drop down our Cop network, and let's dive inside and keep going. I want to bring in my sub geometry with a sub import node. So let's click a use external sub here and let's load it in. And to bring in my attributes, I want to use a rasterized setup node, and here set the space to UVs. And let's also make sure that we're saving the original position, the original P attribute, in a new attribute called RHP. Let's use this with a rasterized geometry node. Wire this in, and I don't want to import the alpha, but I need 2 attributes that I want to bring in. The first will be my normal, and this will be an RGB value, and the second one will be our RHP attribute. Now both of our maps right here are looking a bit funky, and we need both of them quite a lot to finish our setup. What the RHP attribute will encode in the end is simply the position of each point in space, so the X coordinate and the Y coordinate and the Z coordinate. And what a normal node will encode is the normal, but in this case it's better to think of this how much one point or one area or one pixel is facing a specific direction. So the X component or the red component of a normal map right here will encode, for example, how much one pixel is facing into the X direction. And if it's facing exactly into the X direction, this will be a value of 1. If it's facing exactly the opposite direction, this will be a value of -1. With our prep work here done, we can now work on our first big setup. Our first setup will be our 3 UV maps. And for this, I want to work with the RHP attribute. I want to lay down a channel split node, and I'm also immediately going to drop in a channel join node, because what I want to do in here is take the position along the x-axis and the y-axis and the z-axis and turn this into a position along the u coordinate and the v coordinate of a UV map. So to make this node do this, let's set the signature to UV. Now our red component right here will be the U component, and our green component will be the V component. And in here we have our 3 world axes. And now to create our first UV map, what we simply have to do is combine 2 of those world axes into these U and V channels. And for our first map, for let's say our XY map, we're going to combine the red and the green axes like this. And this in the end will give us our first UV map out. Let's quickly preview this. To preview one UV map, we need a map to preview. So let's drop down a file node, and I want to load in a UV test grid, and I can find this under this Houdini picture folder, and I can go 1 level up, scroll way down, and in here I have this UV grid color like this. Let's set the mode in here to RGB, and to use this picture right here of this UV map, I'm going to use a UV sample node. So picture goes in here and a UV map goes in here. We can preview this on our geometry by dropping down a preview material node, and let's maybe make some room in here, and we can copy the sub import from way down here, bring this over to our preview material, this into the geometry input, and wire this into the base color, and as we can see, we now have a first UV map on our object. However, there's still one problem with this map. Looking at it from the front, this looks correct. However, looking at it from the back, our UVs are now mirrored along the x-axis. So this is something that we have to fix. To fix this, what we simply need to do is to invert the x-axis or the U component of a UV map. And we can do this with an invert node. Let's wire this in here. Now the back side is fixed. However, if we take a look at the front, it's now mirrored there. So what we have to do is we have to find a mask for this invert node to make this all work in the end. Clean this up a bit, make this a bit more readable. This is a preview area and this is the area that we're currently working on. To make a mask work, we need a normal attribute now. Let's use another channel split. Let's split our normal attribute into its 3 components. And what we need to do is we need to find the right component. Since we're working on the XY channel here, we're going to use the last remaining channel right here on the normal, which will be the blue channel. And we want to compare it if it's bigger or smaller than 0. So that's why our blue channel into this compare node. And let's set true if it's less than b, so less than 0, a comparison value right here. And if we wire now this into the mask input of our invert node, now the front side looks correct and also the back side looks correct. And what we did is the thing that we need to do for all of our 3 projection planes. This is a bit tedious, so what I'm going to do now is simply bring in the finished setup and then we can take a look at this. So this is what our finished setup looks like. Again, we're still using the normal and the original p attribute, and all of our normal inputs go into a compare node like this. This goes into an invert node as a mask, and then we're using this to combine 2 channels from our RHP into our UV attribute. If you're rebuilding this, the order of what goes in where is fairly important, so do make sure you wire all of this up correctly, and especially down here for the last channel, make sure that the Z component goes in first, and then the Y component goes in. This is the CY plane, not the YZ plane. And also on all of the compare nodes, the first one is set to less than, the other 2 are set to greater than. So make sure you change this here as well. But this should give you all the right UV maps that we need. So this is our second part done. Now let's move on to the third part. Our third part will be creating our masks. There's one slight catch that we need to look out for. So to quickly demonstrate this, I'm loading in a ball as a base object. And what we could, for example, do is simply something like this. We could take in again our normal that we got from a rasterized geometry node. In this case from a wrangle. This is something that we'll cover later. And simply split this to get our separate channels. This will look something like this for a sphere, and then simply take a remap and really crank up the contrast on all of these 3 maps. And what we get out is a mask that looks something like this, a circular mask along one axis. And this already looks somewhat correct. However, if we're going to use this as a blending factor for mixing our 3 projection planes, or in this case 3 RGB colors, we get one output that we don't want, that we don't expect in here, because our output looks like this. The first map that we're blending in, the red map in here, is getting the smallest area, and the blue map is getting the largest area, simply because each circle is covering the last circle before it. This is not what we want. What we want instead is a setup that's a bit more complex, a setup like this, and a setup that in the end will give us a map that, for example, looks like this. It's not a circle anymore, it's a square with rounded corners here on a circle. And what this in the end gives us, if we take a look at our blended values now each color has an equal area, and this is exactly what we want. So this is the part that we're going to rebuild for this. So to build this, I'm going to move my UV setup out of the way. We don't need it for now. And the mask setup that we're going to build here is basically your typical game dev setup, which basically means that it's really, really efficient and fast and elegant, but it's also just a bunch of math. And I want to write most of the math inside a wrangle. So let's drop 1 down and let's set up the inputs on this Copernicus wrangle. Bring up the parameters panel like this. And our first input should be an RGB value, and this should be our normal. Then I want a second input. This will be a mono value, and this will be just some noise to make our blending area between our different UV maps a bit less uniform. These are our inputs. Now I also need 2 outputs, 2 masks. Both of these will be mono, and the first one will be called simply mask A or mask underscore A, and the second one will should be called mask underscore B, like this. Let's wire in our normals and let's also create some noise. For this, I'm going to use a fractal noise 3D input. Again, the 3D input because we don't want UV seams. And this takes as an input our original P attribute and then gets wired into the noise, like this. I also quickly want to build the rest of the setup. The rest of the setup will use those two mask outputs. Let's make them all lowercase like this, make this a bit more uniform. I want to use those two masks to blend between three solids. So let's create those solids, create one constant first. This will be our X constant, and I want to set this to RGB. This should simply be one pure red color, so 1, 0, 0, like this. Then a Y color, so 0, 1, 0, like this, a green. And then last, our blue color, so RZ, and this will be 0, 0, 1, like this. And now I want to use two blend nodes. One first to blend our X and Y, and one second to blend between our first blend and our Z. Our mask A goes into our first blend and our mask B goes into a second blend, like this. And this is our mask setup done. We only need to write the code in here. Let's quickly create a preview for this as well. We still have this preview setup right here. We can for now get rid of a file and sample node, and we can wire the output in here into the base color like this. And now let's take a look at our wrangle and write our code in here. So on my wrangle, there's still two inputs left that I need to create, and this will be two sliders. So for these, let's create two channel floats. This will be our blend main slider like this, and then also our blend noise like this. And I want to save my first value inside a variable called bmain like this, and my second variable in a value called bnoise like this. And let's set this button up here to create our sliders, and for now let's set blend main to a value of 0.1, and let's leave blend noise at 0. Next I want to bring in my normals. I want to save those into a variable called norm like this, and to bring in my normals down here, all I have to write is add n like this. However, this is not quite enough. Our normals are values that are going from -1 to 1. However, for our masks, I want the values between 0 and 1, and I want to have masks on both sides. To create this or to get this, all I have to do is get the absolute of our normals, so make every negative value positive. Then I can create a placeholder for my mask A and mask B. Let's say a float MA and a float MB. And this is where the setup gets very mathy and a bit confusing. So for my mask A, for my MA, this should be a value of norm.y, the y component of my normal, minus norm.x, so the x component of my normal. And MB will be the z component of my normal, norm.z, minus, in this case, the maximum value from either my norm.x or my norm.y, like this. And finally, I can write those out to my mask A and mask B. So at mask underscore A will be equal to MA, and at mask underscore B will be equal to MB, like this. Now, we did lots of strange stuff. Let's actually take a look at how this looks here on a preview material. And as we can see right here, we sort of get a first preview of our masks in here. We have one blue area here, one red area here, and one green area here. The only problem right now is those masks are super smooth because we haven't implemented our blend factor in yet. So these are as smooth as they can be, and we have to make them sharper. So to actually make them sharper, we have to modify our MA and MB. So MA now should also be equal to MA divided by our blend factor, so in this case our B main. And let's do the same for MB. MB is also equal to MB divided by B main, like this. Let's see what this gets us now. This definitely looks better. However, if we try to adjust our masks, as we can see right here, the red mask is sort of growing, and we don't want that. We want all our masks to remain an equal area. So to fix this, before we divide by our B main, we want to add half of our B main value to our MA and MB. So our MA now is equal to MA plus B main divided by 2, and then divided by B main. And the same goes for our MB, something like this. And now if we adjust our blend factor, now our masks are blended equally, which is exactly what we want. And the final thing that we want to do is we want to add our noise to our mask. And for this, we simply want to modify our B main. So B main plus equals our noise input down here. So add noise times our blend noise factor up here. So B noise. And now if we slowly add some noise in here, we can also see some noisiness here in our blends, which is exactly what we want. And this is our masks done. So let's wrap this into a box as well. Let's make this black as well. Let's get rid of our preview down here. And now let's combine both of our UV maps and also our masks into one final texture. Let's bring in a file node, one texture that we want to have on object. I'm going to use one of the built-in ones of Houdini. I'm going to go to the texture folder and I'm going to scroll way down and I'm going to use this wood 001 base color like this. Again, make sure that the type is set to RGB, and let's move this down to our 3 projection planes like this, and let's use a UV sample for all of these. So our texture goes in here and our first UV map goes in here, and let's duplicate this wire in the second UV map, and let's duplicate this and wire in the third UV map like this. And now we should have our 3 projected planes. Now let's bring in our masks. So for this, let's go up here to a mask setup. Let's use a channel split like this. And let's wire in our mask output in here. And let's bring this down to our last network box. And let's use some blend nodes. We want to blend between our first and our second projection like this. And then between our first blend and our last projection like this. And then let's make sure we choose the right mask components. For our first blend, we want to use the green component, the Y component like this. And for our second blend, the X component. And now we get a texture like this. And we can put this in a network box and check this on our object. And yeah, now we have some triplanar mapping going on here. So we're almost done here. The last thing that I want to do is just add some tiny bits that make the setup work just a little bit better. Make it just a little bit more practical to use. And the first thing that I want to do is I want to be able to transform my triplanar mapping. Be able to scale it and rotate it and move it. And this is something that I picked up from Luca Veronese's setup, along with adding some noise to my blending factor. Credit for both of these can go to Luca. And what I need in the end to transform my texture in here is a node that is called vector transform. I'm going to need this both on my RHP variable and my N variable. So let's add some reroutes in here to make this a bit easier, like this. And I'm going to wire in my vector transform into both of those. And on my RHP, I can use the translation, the rotation, and the scale, and also the uniform scale. And on my vector transform on my normals, what I only care about is the rotation, and that the rotation matches our rotation right here. So to do this, let's select our RHP vector transform. Let's right click on the rotation. Let's say copy parameter. Let's paste the relative reference here on our normal like this. And what I can do now is simply go in here to my bottom vector transform. And for example, move my texture along the x-axis, maybe make it a bit smaller, and also rotate it. And all my mask and everything else should react accordingly. So this part is done, and the second part that I want to change in here and the last part is I want to replace this rasterized geo node in here, because this is maybe a bit hard to make out here, but this node is somewhat prone to give you artifacts around the UV seams, which get really apparent once you're dealing, for example, with displacement maps. And thanks to Randalvi, we now have a simple way to fix this, a simple way to build our own rasterized geo node that works perfectly. And for this, again, I'm going to use a wrangle. On this wrangle, I'm going to set up my inputs and outputs first. We're going to have 2 outputs. This will be an RGB value called N for our normals, and an RGB value called RHP for our original P attribute, like this. We need 1 input, and this will be the geometry input. So let's name this geo, and let's set this to geometry, and wire in our geometry in here, like this. And all we want to do in here is basically almost the same thing as a rasterized geo node does. We want to find the closest position on each face of our geometry based on our pixels position. We're going to do this with an XYZ dist function. This takes in our geostream. This will be geostream1 as indicated here. We need our current pixels position. This will be v at p. And then this node or this function will fill out a prim variable and a UV variable. However, we need to create those first. Let's make some room here and let's create an int called prim and also a vector called UV. We can get our v at RHP map out by simply using a prim UV function. Again, we're looking on geostream1. Our attribute is called RHP, and we're looking on a current prim and a current UV position like this. And we can do the exact same thing for our normals as well. So v at n is equal to our normal in here. as well. And now we do get a map that looks very similar to the map that we get up here. The only difference is that the space between our different UV islands in here is filled out, and in here it's simply black. This leads to artifacts, and this does not lead to artifacts. This is why we did this in this wrangle. And then we can finally wire in our normal in here and our RHP in here, and our setup should work just as well, or no, maybe even a bit better. And of course, this wouldn't be a COPS tutorial without one final crash in the end. So let's quickly reload Houdini. And this is it. This is our final triplanar mapping setup. What you could do now is basically take all of this and turn it into a digital asset. The main things that you want to adjust inside this digital asset is, of course, the transforms, as well as some of these noise parameters and those two blend values inside the wrangle. And of course, you want an input for the file node in here. If you're interested in how you can turn this into a digital asset, in the previous episode, I walked you through this, and this is it for today. In the next video, we're going to talk about how we can modify this setup to make this work with a normal map. But until next time, it's cheers and goodbye. And in case you're wondering how on earth I'm allowed to spend 2 whole weeks just researching triplanar mapping, well, it's all thanks to our patrons. They really keep the lights on here. If you want to support us and gain instant access to almost 400 additional episodes, you can do so at patreon.com/Entagma. Also, let me say thank you to all our existing patrons. Without you, Entagma would not be possible. Thank you.